I was going to give a brief introduction, but I don't really know what to say. I've been around for a while in this school. I'm the Director of Studies for Computer Engineering, so if any of you are doing computer engineering, I know about half of you are, then I'm your academic advisor as well and Director of your studies. For those of you that are doing comp sci or software engineering, I don't have anything to do with those directly. They don't talk to me, so maybe that tells you a bit, all you need to know. There is a bit of a divide between computer engineering and computer science, as many of you know. And maybe that's why you're in this room, because this is really where that divide begins to some degree. When we start talking about hardware, not that computer scientists didn't talk about hardware right from the beginning at all. In fact, first there was computer science, and then computer engineering developed. And those two have stood in coexistence for probably 40, 50 years by now. And it's really only much later that software engineering was sort of spawned off as an engineering discipline. So the reason computer engineering got spawned off from computer science is because there's quite a lot more focus on engineering aspects of how systems are designed and built. And I think computer science has traditionally been a more analytical topic concerned with the fundamentals underlying computing, as opposed to actually creating something necessarily. And that's that difference that software engineering identified and has been working on over the last 20, 30 years. As being the creation of software systems. Whereas here we're talking about, well, we're going to begin to talk about how is hardware designed, and I don't sort of mean disk drives by that, but rather, or floppy drives, those of you that can remember what that is, but rather about processors and other useful systems. And maybe you'll get to appreciate at some stage during this course that actually there's not much difference. You know, you can harden any algorithm you want and put it into hardware. And the original computers that were made had a lot more hardened stuff in them. They weren't nearly as programmable. It took us a while to figure out how to do that efficiently. All right. Enough of an intro spiel. I don't really know what more to say. So, look, this course is about, well, introducing you to the design of digital logic, circuits, and systems. And that means you're going to go on a fairly long walk through a whole bunch of fields that have to be drawn upon to some degree to understand how circuits are designed and analysed and how they can do useful things for us. And so we will have to cover some theory, but perhaps even more importantly, what you will be learning in this course are how you implement these circuits in hardware. And we'll be looking at a number of aspects of that. Namely, we're going to learn how to describe hardware using a hardware description language. It's got nothing to do with programming, so if you're here to learn how hardware is programmed, you're in the wrong room. We're going to learn how it's described, and that's a completely different thing. We're going to find out about simulating hardware, learn how to do that, because we need to be sure that the designs that we create are correct. If you get, as I'm going to tell you in a few minutes' time, ChatGPT to design you a piece of hardware, you want to make sure that that design that they've provided you with is correct. Don't take their word for it. And we're going to learn about implementing and testing designs in field programmable gate arrays, so in programmable hardware. And so it's a very practical course, as you'll see, and I'll explain further in this course. So that's what I'm saying here. The emphasis really is on the lab work and learning enough about how one designs hardware so that at the end of the course you actually can create something yourselves, and that's tested through a prac exam with a hurdle ultimately, but we'll get more about that later as well. So we cover the theory that's really necessary to perform that lab work. One could go on and on with the theory, there's no doubt about that, and I literally just cherry pick what you need to know. Okay, so I'm sorry if you love theory, I suggest read the text. It's got lots of really nice explanation in it beyond what I'm going to tell you in the class. What I'm going to do is focus on what you do need to know in order to be able to design hardware. So, what do I mean by logic design? Well, that begs a broader question that I'm sure you all have opinions on. What is design? Anybody have a ready answer to that question? Yep.
Creating something.
Okay. Keeping it very open there. Yep.
Something custom built for a purpose.
Okay.
Building something custom.
For a purpose, I like that. Yes.
Doing something efficient.
Yes, that too. Mm-hmm. How do you know where to start? Yes.
So we have some kind of requirements to fulfill?
Yes. And given that set of requirements, how do you know how to start?
Satisfying your requirements separately.
Sorry, are you the business student? Sorry, I'm just kidding. No, seriously, brainstorming is a good technique, but you've got to know something before you can brainstorm, don't you? Yeah.
Like you figure out what the inputs are and what the outputs are.
Yeah, okay. Well, yeah, because the requirements don't normally, they don't necessarily state that clearly. Thank you. Yep.
You want to start from something that already exists and figure out how to modify that.
That's a really good technique to use. Yep. Yeah.
Just start with the minimal thing that is functional and then build up from that.
Yep. So that's called what? Iterative prototyping, right? Yeah. Anything else? Right. There's a lot of ideas that have come out there. I've got a slightly different definition. It's no better or worse than what's already been proposed. But the main idea is that you sort of you already know what components you can use. Certainly in engineering you usually do. You know, if you're a civil engineer, you've got all sorts of structural elements, mechanical engineer, mechanical elements, electrical engineer, electrical elements. Logic or computer engineer, you've got logic elements, all right? Elements of logic design. We need to know how to put them together and usually need to meet some requirements, performance criteria in terms of size, cost, etc. So you can specialize that definition for logic design. I'll let you read through that. But on top of just being able to put things together, because of the cost considerations and performance considerations, you know, we may have to optimize things, so that means transforming the design that we have already, improving on it in some way. And as far as logic design is concerned, there's lots of different implementation technologies, so figuring out which is the best and trading off the costs and benefits, that can be quite challenging, and people are still writing PhDs about that stuff today. So, where are logic designs used? literally everywhere, right? The real challenge for you young engineers and scientists, is where is it not currently being used yet? And where will it never be used? Because that's where the forefront is, and that's where you want to develop stuff. That's where it's really interesting to be working, right? Okay, so why should you be studying logic design? Well, some of you have to. I've told you, if you're a computer engineer, you have to do this. For the computer scientists, well, I assume you've got some other motivation other than just there was no other course I could pick. I'm hoping that wasn't the reason. Is there anybody in the room that was in that situation? Not prepared to admit it. But you probably want to know something about, well, the underlying hardware and how it comes into being and how is that done. Or at least know enough about it so that you can talk with those computer engineers in a way that they understand and understand what they're trying to do. So these are, I think, really more relevant and important reasons. It's an important counterpart to software design. In the end, software is just a soft version of hardware. It's essential to understanding the efficiency of implementing something in terms of cost and performance. And, you know, if you're interested in parallelism, if you're somebody that likes that, studying it, and have been doing it in operating systems or networks or wherever, this is where you get to experience it on a massive scale. All hardware is parallel. It's all working concurrently at the same time. All right? So this is where you learn a little bit more about that and what that means. All right. Are there any questions so far? Does that give you a bit of a sense of where we're going, or have I just confused you so far about why you're here? Any answers at all? Any? All right. Do you like what you see or not? All right, good. Well, that's good. So I'm hoping that I don't piss you guys off because it's so easily done. All right, a little bit about the formalities of the class, the organisation, etc. As you know, we're in here now, and we're also in here on Fridays, 1 to 3. I did try to turn the aircon on, but for some reason that is not turning on. Don't know what you have to do to get it going. It just says stopped, and that's it. And the instructions here are to a completely different user interface. Anyway, so lectures are in here. Hopefully we can make it less stuffy. There's one way of doing that. I'll just take this up here. I don't know about you, but the airless stuff. Right, the important bits in the third line there. So those of you who came into this course hoping and praying for fortnightly online quizzes, that's not happening. We're doing one midterm quiz. So because the ECOS system still has in the outline fortnightly quizzes, I've got to make this plain and clear to everybody. We've got one quiz, right, on the 31st of March. So please be here at 12 on that day. Now we have 143 people in the course at the moment. There's 106 seats here. I don't know how I'm going to do that yet, but we'll figure it out, hopefully. Right, labs. They start this week, okay? And you'll need a lab kit in order to start. So please pick your lab kit up from the admin office in K17. You all know where K17 is? Level 1, The admin office is sort of to the left of the lift shaft at the end of the corridor, all right? Pick it up between 10 and 4 any day this week. There'll be a rush, so be prepared to wait a little. Is there anything else important? Yeah. Look, this week is important. So you're going to start familiarizing yourself with very complicated software and with initially a bewildering piece of hardware that doesn't look like it really is capable of doing anything. So please go to your labs this week if you can and start working your way through, well, do the familiarization exercises. It's designed for you to be able to continue on in your own time, albeit in order to load the software onto your own home machines, you would need a non-Apple Silicon Mac. If you have one of those, don't even begin to try. It's never going to work. We've tried, believe me. So it's best to pick up a cheap, old, IBM compatible of some form or another IA86 machine of whatever brand, doesn't really matter. The more memory it's got, the better, and load it up on that. So look, what's really important here to some degree, although it's sort of lost here, maybe it's better to talk about it on the next slide, which is the assessment slide. Right up the top there, 40% lab, there's 7 submissible lab exercises, and altogether they contribute 40% of your marks. So there's a lot to be said about it, I guess. There's 7 lab exercises in 9 weeks effectively, given in week 1 you're just familiarizing yourself, so that doesn't leave a lot of spare time. Unfortunately, if you want to learn how to design hardware, you have to go through a series of steps to do that. We've covered it in these 7 lab exercises. We think they're enough to get you going pretty well. But you only have like 2 spare weeks overall in the term. So the best thing to do is try to get that lab done the week you start doing it. If you let it go, things will start piling up and you're not going to catch up effectively. So this is pretty important to try and just stay on top of things. There's a 15% quiz, as I mentioned, 45-minute in-person quiz. It'll be closed book and it'll be invigilated, right? So to avoid the cheating, etc. Of course, I can't avoid you seeking whatever help you want for the labs. And at the end of the term, there's a 15% theory test, which is open book, so you can bring any materials along. It is invigilated. You won't have a network available to you. You'll only be able to use the lab machine for that. And finally, a 30% prac exam. Yes?
Is the midterm quiz theory or the factual?
It's theory. It's just theory. It's just 15 multiple choice questions.
And also the final, is the practical immediately after the theory? Or
It is. Traditionally, we normally give you like a half-hour break between the theory and the prac exam. So it's in a 4-hour block. I know there's probably a few of you that might not like that and have, need me to make other arrangements, and I will make other arrangements for those people. Does that answer your questions? Yeah, good. Importantly, this prac exam has a 40% hurdle. You've got to get 40% of the marks in that prac exam in order to pass the course. Okay, so this is where the really hard facts have to come out. I'll spell them out once. Last year, I think I had 100 people sitting the final exam. 11 people who would have passed the course otherwise failed because they failed the prac exam, the hurdle. They didn't pass this hurdle, right? So they got a UF. There was another 20-odd that failed the exam and would never have passed the course even if they had passed it. So that all up is between 25 and 30 people that failed. Mainly because, and I guess the other stat that's important to note is, of those 11 that got the UF, their average lab mark was 73%, and their average prac exam mark was 25%. So you go do the sums. You tell me how that happens, all right? Don't rely too much on using other people's work if you want to pass the course, and that's really something I spell out here on the next page. If you want to pass, you'll have to do your own lab work in order to understand what's going on. Otherwise, it's not going to work. All right? So this is really important. You can ask others how they've done it. Do that by all means. That's a really important way to learn, is to ask others, how do you do this? But in the end, you've got to do it yourself. You've got to submit your own answer. You've got to make the effort to write it up yourself. If you just take their file, put your name on it, and submit that, I probably won't notice because there's too many to mark. But you're not going to learn that way. And if you do that too often, you won't know enough to pass that final prac exam. All right? Have I scared you enough? Is that sunk in? Good. Get the labs done each week, and that's because they start piling up if you don't get through them. So I think it's better spend the extra effort and get it done within the week that it's set, rather than waiting the 2 weeks before, just before the due date, submitting it, when you already burnt the first week of your next lab, which really doesn't help you. Take responsibility for your own learning. Obviously, you know that. It is a demanding course. There is a lot of material. It's possibly a little unlike other courses that you've done. The information content is dense. Not that that's so different, but it's in a completely different direction to what you're used to doing for many of you. So that's the challenge. If you want to, though, understand how digital systems are designed and how they work at the gate level, then this is where you'll learn that if you do what I recommend you do. All right? Yes?
Yeah, this person like the final theory exam, the practical exam with open book. So
Yes.
what does that mean? Like, are we supposed to...
You bring whatever lecture notes you want with you. You can download the internet if you can onto your USB thumb drive. You're allowed to bring in a thumb drive. You're not allowed to bring your own computer in. You're going to have to use the lab computer for it. So get experience with using the lab machines, because that's the environment you're going to be using in the exam. Yes?
For the midterm quiz, are there like theory practice?
There is. I've put exam practice papers already up there. So there's a practice quiz paper, there's a practice theory paper, and there's a practice prac exam. If you can do that now, you know you're going to be pretty well set for passing the exam at the end. Are there any other questions? Yes?
In previous terms, the lecture notes and the textbooks from the chapter, the chapters from the textbook, there was a mapping between them.
Yes.
Yeah, is there the same? Is there the
No.
same table for this?
No, I haven't put a table up. I think sometimes I do make it clear which part it comes from. The main difference is I developed the notes for third edition of the book. There's now fourth edition. You can't buy the third edition anymore. I have a copy of it, but I haven't yet gone through it to see, well, what does that map to in terms of the chapter number, etc., what sections. But from having a very quick flick through the book, I think they moved one chapter to the end. They've done, in fact, what I've been doing in my course. They used to have this early chapter on how gates are implemented at the transistor level, and I just think that that's too unimportant for when you want to design circuits. So I do that in my second last lecture, effectively. And they've moved that to the back as well. And I think the rest was pretty much the same. So I don't think there's going to be much of a difference. Does that help answer your question and help you with? finding the stuff, but I will try. There's lots of other things to do to put up a mapping for the 4th edition of the book. There's probably more PDF versions of the 2nd edition floating around though than of any other editions. So, and I don't have that copy, so I don't know what the mapping is for that. All right. Any other questions? We effectively do, like each one of my lectures essentially maps to one of the chapters in the text. Essentially, this one was based on the original 1st and 2nd chapter in the text. So just a note about cheating. I think I've stressed it enough. I think this bit's also important to mention that, look, contrary to software design, generative AI isn't doing that well on hardware design yet. There's a couple of reasons for that, I think. I don't really know the right answer either, but I think in contrast to software, where there are billions, if not trillions of lines of code out there for AI to munch through, there's very few commercial hardware designs out there, that have been open sourced and made available for a start. So all that's there is really what students have posted as their solutions to, pretty mundane questions that we raise as lecturers. So there's probably not enough background material for AI tools to really get into and understand enough to tune themselves properly. So I think that's my reason. If Hammond were here, he'd have another reason, I'm sure, for those of you that know Hammond already. For those of you that don't know him, if you're a computer engineer, you're going to meet him sooner or later. He has much more perspective on AI than I do. But I don't think it's really ready for digital design yet. And I really don't understand anyway how anybody can learn design from AI. Have any of you learnt anything design-wise? You have to know a lot already in order to probably learn something about design. And I think that's the challenge here. You're being asked to create something from nothing. So how do you do that? How do you do that systematically and effectively? So feel free to use whatever tools you want. I'm going to see how well you adapt or adopt them and how well you put them to use. Okay. So this is the text that I've already made some reference to. So it's the 4th edition. I've put links to it on the web page in the lectures section of the website. All right, that's the background. How do you all feel? All right, it might be a good idea to have a break right now because the next 20 slides, which is what I want to get through today, are going to be a bit more fast-paced and are going to be, we want to sort of look at them as one unit. It's probably better to have a break right now for 5 minutes, and I'll start again in at 20 to 1. Don't have a clock here anywhere, do we? Looks like there used to be a clock there. Any questions? Yeah? Yes. If there's a seat. I mean, obviously, people that are in a lab have first priority. But believe me, after 2 or 3 weeks, only half come. So I don't think it's a problem. Sorry? Submitting the labs is expected. It's not mandatory to attend anything. We can't force you. Who has some previous logic design experience? Anybody? Nobody been designing their own chips yet? What about circuit boards? Yeah? Well, you need to know something about logic design for that, don't you? So what do you know? Are you able to say? What have you learnt through designing boards? Anything worth mentioning? Yeah?
I did design for COMP and design project A. So got around that just because basically I just learned lots of stuff from scratch.
Right. So you've already done design project, have you?
And then I've come back.
Okay.
But
Well, you've probably learned quite a bit then.
yeah, are we still using? Because currently I'm doing 6120 with an hand right now,
Mm-hmm.
and we're currently changing to Verilog, I think, which is very interesting.
Mm-hmm.
So
Well, that's good.
yeah. What's the difference between the two?
All right, I have a slide about it. It doesn't go into the differences really. Verilogs, so firstly, they cover the same concepts. They're both hardware description languages. Verilog's a little bit more Pascal-like or C-like in its syntax. Say again?
I thought because I feel like from what I just had a lecture or a class as well, and it's kind of there's a bit of Python as well that's integrated. While my understanding of VHDL is very
I wouldn't know that. I don't program in Python, but it is a bit more. It's definitely more terse language, but the concepts that are covered are exactly the same. So being able to describe some component in terms of its inputs and outputs combinationally, and also sequential elements can be described, so flip-flops and so on, to remember stuff. Conceptually, they're the same. Different language though. So Verilog's preferred in North America as a design language. VHDL is very much preferred in Asia and in Europe, and in Australia. So years ago we made the decision that we'd teach VHDL. If you want to learn Verilog, you can take the same course effectively in electrical engineering and learn it using Verilog. Won't do quite the same sort of lab exercise. It won't have the same lab experience, but the same content is covered.
yeah, right. And what's the difference between, because there's also 2141?
Yeah, that's Select 2141. That's the same. It's the analog of this course. Using Verilog. Yeah.
Oh yeah, I saw something along the lines of block diagrams in some images on the internet. I was like, how does that differ from VHDL?
Block diagrams.
Yeah.
Okay, well, I've got 2 minutes to tell you about them. So I don't really know what you mean by block diagrams versus VHDL. I assume what you mean is schematic, like using logic circuit diagrams rather than VHDL, which is again a good question, and again it'll come up very shortly. Yeah, so traditionally, electronics designs were laid out as a logic diagram. The problem with that is you're very limited in terms of the scale of the circuit that you can describe using a logic diagram. And it's hard to modify the diagram. It's hard to port it and edit or copy it and reuse part of it. So a language is much more effective from that perspective because it's a one-dimensional sort of description of entity, like, or a one-dimensional design. It's very easy to cut and paste, modify it, port it, add comments to it to describe what it's doing, etc. So that's why a language is preferred over, apart from the scale that you can then apply it to. All right? Okay, let's make a start. So let's begin. So we're talking about logic circuits that are implemented usually as electronic circuits, which in turn means they're implemented using transistors, which are switches, voltage-controlled switches, or three-port devices is another way that they're described. And you know, if they're digital, then you have signal values that are discrete. And usually we're concerned with binary logic circuits where you only have two values, 0 or 1, for a signal, be it a voltage or a current. And so that's what we're really focused on, as opposed to analog circuits, which can also be built with transistors, but have continuous voltage or current signals. And therefore, you know, you can take on a real range of values, and that's why an amplifier, an audio amplifier, for example, is an analog sort of electronic circuit usually that allows you to amplify a signal. Anyway, we're going to consider binary digital circuits, and they dominate because they're simple and easy to manufacture, and they are no less powerful than ternary or decimal digital circuits, each of which would have more means of describing the signal, more values that you could use, but the difference in size is insignificant. The difference in complexity is insignificant. So it's easy to show that binary is just as powerful as any of the other possibilities. So historically, we settled on a binary system. So the simplest binary element is a switch, right? And some 30 years ago, this might have been called a course in switching circuits or something like that. And a switch can have two states. It's either open or closed, and we'll define that in terms of some control variable x, which is either 0 when the switch is open or 1 when the switch is closed, and depict it, let's say, as a box with an S in it to indicate that it's a switch with this x control variable. And then we can build more sophisticated circuits with that switch. We can incorporate it into a voltage-controlled light or a circuit that controls a light, whereby if the switch is open, then there'll be an open circuit, and therefore there's no voltage difference across the light. It's 0, and therefore the light would be off. But if x is 1, there would be a closed circuit between the battery and the light at the top, so you'd have some positive voltage there, and 0 at the bottom, and therefore there's a potential difference across the light. It would light up. You'd get some current flowing across it. And so we can say that the state of the light is determined by x. It's if x is 0, the light's off, and if x is 1, the light is on. All right, we can also represent that slightly differently, so in subsequent diagrams we'll use this notation a little bit more because it's more akin to how you draw electronic circuits. So then there's two combinations of switches that are really important. The first is if you have two switches connected in series, then both of those switches need to be closed for the light to be turned on, right? And that defines the logic function AND. We need x1 and x2 to be 1 before the light is on, right? If either one of them is off, or if both of them is off, the light's going to be off because there'll be an open circuit there, right? So here the dot represents the logical AND. There's many other ways of representing that. Other texts might begin by saying that's a logical conjunction and use an up arrow symbol instead of a dot, but we'll just use the dot to represent an AND. The other important combination is if we place two switches in parallel, then either of those switches has to be closed for the light to go on. However, if both are open, then the light's off. So there are 3 out of 4 possible conditions where the light is on, namely when x1 is closed, or x2 is closed, or both are closed, right? And that corresponds to the logical OR. So the plus here isn't an addition, it represents logical OR. And as I mentioned for the AND, one could use logical disjunction or an upside down or a V to represent that. That's common as well, but in our case, we're going to use a plus symbol to represent a logical OR. So it doesn't mean we're adding one argument to the other, one of the terms to the other. It just means that either one of them needs to be true for the two of them to be true. Okay? Any questions so far? In that case, it should be reasonably straightforward for you to figure out how you would describe the light equation here. The light is now a function of 3 switches, 2 of which are placed in parallel, and then that's in series. That combination is in series with the 3rd switch, X3. So I hope you can see that in order for the light to go on here, we have to have X3 closed, because if it's open, there's no way you're going to have that light turning on. But on top of that, we have to have at least one of these 2 switches to be closed as well. So that means that we need to express this function as X3 and the logical OR of X1 and X2, right? So how many possible states are there for this circuit?
8.
Yes, 8. There's 3 switches. Each one can have 2 possible settings. So it's 2 to the power of 3, which is 8. How many of them lead to the light being on?
3.
Somebody's very quick off the mark here. 3. We need X3 to be closed, so that's half of the situation, at least half the cases wiped out, because when X3 is open, that doesn't work. And then we need at least one of these guys to be on. There's 3 out of 4 cases there, so it's 3 in total that lead to the light being on. Right, good. So there's one final logical operation, fundamental sort of basic logical operation that we need to know about, and that's inversion. In this circuit, the switch is wired across the light, and that introduces an interesting phenomenon. When this switch is open, then there's a current path from the power supply through the resistor, through the light to ground, so the light must be on. But when the switch is closed, then the voltage at the top round bubble and the voltage at the bottom bubble, now I have this pointer, I may as well use it. So up here, VR, let's say, and down here, VG, let's say. If this is closed, they have to be the same. So there's no voltage across the light, and therefore no current flowing through the light, and therefore the light is off. So here, Lx is equal to not x. When x is 0, the light is on, and when x is 1, the light is off. Okay, so it's logical inversion. We can represent that many ways. It's called complement as well. Often with an we will most usually use these 2 representations, either a bar across the x to represent the complement, or a tick at the back. Bit less easy to read, but it's equally valid. These are also possible. These are all commonly used. Okay? So all up, we have 3 basic operations for a switch. We have the AND operation, where 2 switches are combined. The possible states of the switches are listed here in the left 2 columns. This is a so-called truth table, where we consider all possible combinations, all 4 here. The AND function, the OR operation, and the complement or not operation are listed there. Are there any questions on this table? You've all seen this before, presumably. I see many of you yawning, so I'm hoping I'll make it more exciting very quickly, very soon. So there's also a logic symbol corresponding to each of these operations. At the top here, this is the symbol that we use for an AND operation. It has a flat back and a rounded sort of right-hand side. This is the AND of two inputs, x1 and x2. This gate over here illustrates the AND of n inputs. That's a logical symbol. In practice, we rarely put more than 4 inputs into an AND gate. Doesn't work transistor-wise. You drop too much power if you try to do that. Here is the OR symbol. It has a curved back as opposed to a straight back and a somewhat more pointed right-hand side. And similarly, we can extend that up to n inputs. And finally, the complement has a buffer. So without that bubble, it's just a buffer, this triangle, which is just an amplifier. But with the bubble, that means change the logical sense of it. So this turns a 1 into a 0 and a 0 into a 1, right? So that's a NOT gate. All right. And then we can build networks of these gates together. So for example, that circuit that we figured out before that had the 2 switches in parallel in series with the 3rd switch, that could be represented by this logic diagram up the top here. I hope you can see that. So we have x1 or x2 being ANDed together here with x3 to provide this function. Right? Okay. All right, so I'm going to introduce an important point here. So the 3rd dot point there, that the complexity of a given network in terms of the number of gates and the number of inputs to those gates, the total number of inputs, that defines or it has a direct impact on its cost. And given it's an engineering discipline, we're concerned with keeping costs to a minimum, right? So in order to reduce manufactured cost, we seek ways to implement logic circuits as inexpensively as possible, right? Otherwise, you wouldn't get phones for $2,000. You'd have phones for $25,000, right? Smaller, simpler circuits require less transistors, so less silicon area, ultimately, which means less chance of a fault in that silicon or a flaw in it, and therefore a higher yield as far as your silicon is concerned. So that's really important, less transistors. And because you've got fewer transistors and the circuit area is smaller, distances are smaller, so the circuit operates more quickly. Okay? And since you've got less transistors, you need less energy to power it. And because there's less transistors there, it's less likely to fail. So lots of benefits accrue from having the simplest possible circuit, the simplest possible implementation of the circuit. Right, I think you've all understood that. All right, so on to another concept, which is really, given a circuit diagram, how do we figure out what it does? So here's a circuit diagram. I'm sure you can see that here the output F is just the OR, the logical OR of A, the signals A and B. And in turn, A is just the complement of X1 and B is the AND of X1 and X2. Can you read that at the back? You've got better eyes than I do. All right, so we know what the function is. It's not X1 or X1 and X2, right? How do we know how that behaves? Yeah.
When you write not x1 plus x1, x2, how do we know whether...
Or,
Sorry.
let's get into the language. It's or.
How do we know whether it's the AND or the OR is first in the order operating?
That's a good question. When it's drawn like that, the AND binds more tightly, and the NOT binds even more tightly than that. But we'll see in a moment, the VHDL doesn't care, and you have to use parentheses. All right? Okay. So how do we know how that circuit behaves? How are you going to figure out how that circuit behaves? Yeah.
Timing diagrams?
Say again?
Timing diagrams?
Yeah, that's one possibility. So timing diagram, as we'll show in a moment, applies a signal to x1 and x2 and over time varies those signals, and we'll see what the output is. But to do so systematically, we have to go through all possible input signals. Yeah? Sorry?
Truth table.
Yeah, that's also possible. But ultimately what we need to do is apply a particular signal value to each of the inputs and determine what the output value is going to be. Only when we apply a certain valuation to these variables can we possibly evaluate what the function is, right? And we can do that for all possible input signals here. So 0 and 0, 0 and 1, 1 and 0, 1 and 1. We could list it as a truth table then, what the output of this function is. It's not very obvious what that is. Or we could perform or derive what's known as a timing diagram. These are usually output by an oscilloscope. If you apply the inputs x1 and x2 in this manner, and here it's been done systematically because x1's period is twice that and half the frequency of that of x2. So we see x2 varies 4 times whilst x1's only varied twice, or once versus twice here. And we can derive what A and B is. Normally this would be done by probes that you're using that are monitoring what the signal values are on the various wires A, B and F here. Yes?
Small question, but how do you choose how you vary the voltage? Only know the signal. Like on top it has 0011 and the x2 has 10.
Yeah. This is a clumsy way of representing over time what the different values are. All you really need to do is go through all possibilities. But to do that, you have to be systematic. If you've got n wires, how are you going to do this? There are 2 to the n possible combinations that you could be, and so it's going to take you at least 2 to the n steps. You don't want to go over 2 to the n steps, so the easiest way to do this is to apply a signal of a given period to the first wire. Halve that period, or double the frequency, and apply that to the second wire. Double it again and apply that to the third wire, and so on. And that way you'll go through all possible values systematically, as we've done in this timing diagram. And that way you'll get to list systematically also the values in the truth table, which in this case have a binary analog, obviously 0, 0, 0, 0, 1's 1, 1, 0 is 2, and 1, 1's 3, right? So they are sort of systematically listed here. We can see that these ways of analyzing the circuit are equivalent. When we apply the input 0, 0, that's the same as looking at the first part of this timing diagram here, or the first row in this truth table. Similarly, the next possible combination of x1 being 0 and x2 being 1 is represented by, and its consequent impact on A and B and F is represented by the second row in the truth table and the second part here of the diagram, and so on. We can work our way through them. They're equivalent ways of analysing the circuit. Normally, from a theoretical perspective, we won't have access to an oscilloscope, so we would normally just list the possibilities using a truth table if the circuit's small enough to allow that to be done. All right. But take note here. Here's another circuit, different from the one at the top, and yet it has the same behavior for the same set of inputs. We have the same output G for F there, and yet it does away with the AND gate, right? It does not include the AND gate, yet it has the same behavior. So this is a cheaper implementation of the same circuit, right? And what we're going to learn in the next couple of hours is how you can systematically figure out what the cheapest implementation of a circuit is, what the best from our perspective is. All right. So we now know that digital circuits are implemented using transistors. There's two types of circuits that generally are manufactured. They're either custom, which we heard mentioned previously, or they're a standard component. And usually the custom circuits are fixed. They might have some different modes of operation, but they're generally not used for general purpose applications, so they're not generally programmable. Whereas standard components, ones that you buy off the shelf that include things like microprocessors, right, they're programmable. And we'll be using field programmable gate arrays here. They're all standard components because once the design is, we've figured out what the layout of the transistor should be, you just manufacture that and you sell it en masse, right? And it has lots of different applications, whereas these custom chips, they usually have application-specific uses, very much smaller market share generally. All right, so we're going to talk a little bit about field programmable gate arrays because that's what you're going to be using in the lab. And in fact, this is the chip that you'll be using, an Arctic 7 from Xilinx, which is now a company owned by AMD. And it has a ball grid array on the base that allows it to be wired into a circuit board. These FPGAs are programmable, and I'll show you how. They can essentially implement any digital circuit that will fit within the device. So you can buy them in varying sizes, although the largest in no way could fit a complete, i7 processor into it or a GPU of any type whatsoever. They're just way smaller because there's so many programmable components within an FPGA. There's very few transistors left over to do sort of useful work. So internally, they comprise a 2D array of configurable logic resources. They're represented by these orange blocks here that you see. And then a two-dimensional grid of wires that allow you to connect them together as you need to connect them, all right? So to configure a circuit into the FPGA, we have to tell each one of those configurable logic blocks what its function is. And we have to say how should the wires be connected together. And that's known as a configuration of the FPGA. And this is provided as a file that has to be loaded onto the device before it will perform any useful work, right? Okay? And this configuration file, in turn, is produced using computer-aided design tools or electronic design automation tools. Okay, and we'll go on to speak about that in a moment. But are there any questions on this so far? Right? Yeah?
So to my understanding, QHDO, you describe FPGAs using that, but some other language does the configuration process that we can stop, or is it the same?
Right. Yes. So there is actually a very complicated stack of software that sits on top of hardware like this. You'll get to experience a tool called Vivado, which was designed by Xilinx to program these chips. So every chip manufacturer provides their own tools to map designs to their device, all right? To program that tool, though, we use the language VHDL. You could use Verilog. It has to be one of those IEEE standard languages. And that allows your design that's written in VHDL to be taken from one device and put onto another by just using the tool flow then that targets that vendor's device, as it were. So you're going to be learning about VHDL as the input language to this tool called Vivado. Is that what you're after?
So what we write is just the input that gets fed into the model?
Yes.
And so in industry, do all the engineers that work on FPGAs do the same thing, or do they also do stuff with Vivado? Is that something we have to
Yeah, that's a good question. And we'll actually have somebody coming along on Friday, well, they'll be coming along virtually, from Optiva to talk about what they do. They're just going to be introducing themselves on Friday, and at the end of the course they're going to come back to give a guest lecture on how what you've learned applies to how they do things at Optiva. But yes, Vivado is an industry standard tool. Many companies use the AMD Xilinx tool flow because they use Xilinx chips. Other companies use the Intel Quartus Altera design flow because they use Altera chips that were bought by Intel 20 years ago by now. Not quite 20 years ago, but a long time ago. In fact, Intel spun them out again and no longer producing FPGAs. But the two main manufacturers used to be Altera and Xilinx. They're both taken over by big companies. They're the industry standard operators. The only difference is that some houses will use VHDL and others will prefer Verilog. So you'll learn VHDL, and with a slight mind shift, you'll be able to apply the same principles to Verilog. Okay? So it'll be directly applicable. Any other question? Yeah?
What are exactly are the use cases for FPGA? Because you just mentioned that they're not as good as normal.
That's a good question. So the custom, to produce a custom VLSI chip is a very expensive business. It's probably on the order of, I don't know, $50 to $100 million to start producing custom VLSI chips. To produce a design that you know is correct, to fire up a foundry, to then produce the semiconductors with the right design on them. It's a very expensive process, and most of the cost is in the design, in the testing, to make sure that it's correct. Because if you stuff it up, you've burned $100 million and you have nothing to show for it. So, in applications where the quantity, in order to make that worth it, you need a very large market. So mobile phones are great because they're a large market. You can have lots of custom VLSI chips manufactured for them, but it doesn't go some way to explain why they're so expensive, because we have a lot of really expensive design that's gone into it, design and test. Other sorts of markets where custom VLSI works is TVs, entertainment systems, consumer electronics, fridges, washing machines, microwaves, as well as cars. They're very important as well. And you know that during COVID, all the silicon chip suppliers shut down. No cars were manufactured anymore, right, as a consequence. But there's lots of problems where the market isn't nearly as large and cannot justify investing that amount of money. And so they're sort of either completely one-off, which might be defense, or NASA-like projects where you don't have many, or satellites, or list goes on. Even base stations, a lot of them would use FPGAs, even though they could be probably justifying using custom VLSI as well. Big scientific experiments like the Large Hadron Collider make use of hundreds of thousands of FPGAs in their experiments, right? And the reason they use them usually comes down to a few things. They need high performance, they need low energy consumption. And they're the two areas where FPGAs can outperform custom, or can outperform processors in any case. As you know, GPUs use a lot of power. So if you only have 10 watts to play with, forget about GPUs. You can't use them effectively. Okay, maybe you can use Jetson Nano or something, but even then, not very realistically. So wherever you're power limited and still need performance, FPGAs come in. Now we better get a move on because I've got to finish this lecture as well. But does that give you some answer to your question? All right. Let's keep going, and I'm happy to answer more questions at the end once we make it. So this is the board you're going to be using, the one that you can borrow from, or you borrow it for the term, you'll be taking it home, you're responsible for it. Please return it if you drop the course, because we have a wait list currently. We need to recycle these, and obviously, you know, a board like this costs us $200. If we lose it, that's a hole in our budget, so we need them back. All right? So here's the FPGA in the middle here, actually. It's here. That's that RTX 700 that I was telling you about. There's a pile of switches here, and there's some, and there's LEDs along the bottom here, and there's these 7-segment displays, and there's some push buttons here, and they're the main things that you're going to use to program, or to rather interact with the FPGA once you've loaded it with your design, to make sure that your design is correct, you know, to test it. Okay. Now, so I told you about those configuration files. How are they produced? So this is a schematic, looks sort of dated, but it's accurate. This is how things work. Generally, you have some idea for a design. You start with some requirements, and then you need to specify how are you going to implement that design. And we've already talked a little bit about the two alternatives, either a schematic capture where you draw the diagram by hand, and or using tools and input into the rest of the flow, or you use a language, a hardware description language. And that's the route that we're going to take. I'm just going to have a bit of an aside here. So HDL is a common acronym for describing hardware description language. It's like a computer programming language. It looks a bit like one, except that it's used to describe hardware, and it's the describe bit that's important. It's not meant to be executed on hardware, okay? It's more like a markup language, if you like, from that perspective. So it's to describe hardware, it's not for instructions that are to be executed on a processor. So we're going to study one or two IEEE standard languages. The one we're going to study is VHDL, and that stands for, actually the V is actually short for VHSIC, Very High Speed Integrated Circuit Hardware Description Language. That's what VHDL stands for. And the other one is Verilog, which I've made some comments about previously. Needless to say, when you have described your design at the top here, that then gets passed through a compiler effectively, although there are other names given to it. Synthesis tool is common, to synthesize what's known as a netlist. And a netlist is a logical description of your circuit. Think of it as a circuit diagram. That's all you really need to know. That's what's generated by the compiler when you synthesize, when you go through the synthesis step. To check that you've got the design captured correctly, we then perform functional simulation. And what that normally means, or in our case will mean, is we're going to simulate the design. We're going to provide a set of known inputs to your design, your circuit, your design, and observe what the output values are. And hopefully they're correct, because if they're not, then you have to change the design in order to improve the output, right? To converge on what the desired design is. So if the design is not correct, you've got to go back to modifying the design that you've specified. However, once it is doing what you want it to do, then one goes on to figure out, okay, I have this logical representation of my circuit. I know what functions need to be implemented and how they're connected together. The tool has to then figure out, how am I going to lay that out on the FPGA? What's the most efficient way of laying that out? Because if you use sort of random locations, the wires might be longer than they need to be, or you might end up using more lookup tables, configurable logic blocks, than you need to if it's not optimized. So this physical design step maps this logical design to the physical resources that are available within the FPGA. When that's done, you can simulate how long it takes for signals to traverse the wires in the design. This is still a simulation. And confirm that it performs as desired. If it doesn't, you'll need to modify the design in some way. But if it does, then you can produce a configuration file, load that onto the device, and actually test it in situ, in silicon, on the FPGA, and check that everything's performing correctly. So it's quite a long process, and the CAD flow, the CAD tool that you'll use performs all of those steps in sequence if you follow the instructions on how to use it. But it is complex, and there are many parameters that you can tweak to change the way the design gets interpreted and mapped to the hardware. Are there questions on this? Okay. In that case, let's move on. Just a couple more comments on VHDL, which were raised in the short break, but not everybody was here. Instead of using a circuit diagram, using a language like VHDL has several benefits. It's plain text, so you can edit it easily, whereas you can't edit a diagram very easily. If you want to change a gate in the middle or need to change several, how do you rub that out and put them in? It can be difficult, given it's a two-dimensional construct rather than a one-dimensional construct. It provides design portability because it's a standard language, and that means every vendor's tools will have that synthesis tool available for it. So you can take a design that's been designed for a Xilinx FPGA and port it to an Altera FPGA just by taking the code, all right? So it's also important because the implementation technology changes rapidly. Not only do you have portability between vendors, but even within the one vendor, you're going to be wanting to go to the latest version of the FPGA, and that means re-implementing the design potentially. And finally, you know, you could, because of all of these factors, it's easy to use the code, it's easy to share the code, and that all aids productivity, which is important, an important parameter in designing hardware. Are there any questions about this? It should be pretty straightforward. Okay, so let's have a look at what VHDL looks like, and I'm going to introduce it with a very simple design. I'll show you a second design and introduce another concept, and finally we'll go through an exercise of doing it ourselves. So, a VHDL design consists of two bits of information: the so-called design entity, or the entity declaration, which tells us what the circuit looks like from the outside, and the architecture, which tells us what the circuit looks like on the inside. So let's have a look at this entity declaration first. So you can imagine that essentially you put a black box over the circuit, and we only care about what are the inputs and the outputs to the circuit, and that's what's just declared here in the entity declaration. Couple of points here. Signals of type bit here can only have a value 0 or 1, which is okay for today, but it won't last us very long. We'll have to be a bit more sophisticated shortly. There's a so-called mode associated with a signal. Is it an input or an output, or is it both? And there's something about the language itself. You know, the identifiers that you use have to be alphanumeric. And you're allowed the underscore as well, and you have to start with a letter, effectively. Yeah.
Here the bit is a data type.
Yes. Yeah, the bit is a data type. Okay, let me make something clear. I'm not a computer scientist. I'm not even a computer engineer. I'm a teacher. But I don't actually know enough about VHDL to do a very good job at teaching VHDL. I'll be teaching you by example. So if there's something that doesn't make sense, just let me know and I'll try to clarify. But I'm not going to cover all of the possibilities that you could encounter in VHDL. I will teach you enough so that you should be able to read VHDL. Okay? Okay, that being said, let's have a look then at the architecture of a VHDL design, which describes either the structure or the behavior of what's inside the circuit here. And this here is actually a structural description because we can see that the output F is defined in terms of the inputs X, 1, 2, 3 via these logic gates, and they're wired up a certain way. Here's our architecture, and it involves a simple signal assignment statement there, which tells us that F is assigned X1 and X2, or not X2 and X3, and we don't really need to know more because VHDL knows what NAND gate is, it knows what NOR gate is, but it doesn't know how you want to combine them, and therefore you need to use parentheses because these all have the same sort of the same precedence, and therefore we need to parenthesize to show what we mean. All VHDL statements need to be terminated in a semicolon, hence that one there and this one here. And as I mentioned, we don't have that precedence, so we need parentheses. I don't know that there's anything else there, so let's have a look at the whole thing. Here's the whole shebang, the design entity for that circuit. The design entity comprises both the entity declaration and the architecture all together in one file, and that's it. In our lectures, we'll use capital letters for all the keywords, so entity and is and port, in, bit, out, architecture, and or not, of are all keywords, and all the lowercase ones are ones we've defined, user-defined names here, okay? VHDL is not case sensitive, that's important to note. Let's have a look at a second design, that's this one here. In this case, we have 4 input bits, X1 through X4, and 2 output bits, F and G. So slight variation on example 1. And the architecture, of course, has to now describe how both F and G are derived. And you can check for yourselves that they're listed properly. Now I want you to observe, if you wanted to analyze this circuit, what happens if we start in this state where X1 0, X2, X3 is 1, X2 0, X4 is 1. What happens if we change X1 from 0 to 1, right? Then clearly the output of this AND gate goes from 0 to 1. And given that the output initially of this AND gate was 0 as well, so F would have been originally 0, it'll go to 1, right? And you can make a similar argument to show that G also will go from 0 to 1. So what order should things happen in that description? Should we evaluate F first, or should we evaluate G first? Same time, good. Yeah, they're examples of concurrent assignment statements. All assignments are concurrent. So the order in which we list the assignments doesn't matter. So this is different to a programming language where normally the top to bottom sequence of instructions indicates a temporal sequence of how they should be evaluated. You always evaluate the first statement before the second statement, or it should be in terms of its logical sense. But this is a description, and as a description it doesn't matter what order, because we're not describing the order within which things happen. What we're describing here is the functional output. Okay, so whenever there's a change in one of the signals on the right-hand side, the implication is that that signal has to be re-evaluated. That output has to be re-evaluated. But that's not done by the compiler or anything like that. It's done by the hardware that this description is describing. So we've got to go through that process of synthesizing the circuit first before that becomes true. Okay, and all this is saying is that F and G are both combinational signals and they're going to be evaluated at the same time. So they have inputs coming at the same time. In this particular case, if paths that go through the NOT gates have to change, then that's going to take a little bit longer than paths that don't go through the NOT gates, for example. More on that later. All right, so thankfully we've made it to the exercise and we've got half an hour to spare, so that's very, very good. Are there any questions so far on what I've been talking about here? Let's just deal with those first. I think I've exercised your minds enough. You're tired. For a Tuesday, first day, second day back to uni, it's pretty hard. All right, so here's a timing diagram for a 3-input circuit. X1, X2, and X3 are inputs, and F is the output. Are you able to determine what the truth table is for this function? And can you describe it in VHDL? I'd be very surprised if you can do it in your head, unless you've had experience at this before. You've got to be systematic about it. So a good way to start for a problem like this is to list it as a truth table, because we find it easier to look at symbols than we do to look at a graph and figure out what that means. So in our case, we might just write that out. All possibilities. I think it's 0 that 1 that changes the least quickly. So right, they're the 8 possibilities for F. So what's the value of F when all 3 inputs are 0?
1.
Right, and then?
0, 0, 1, 0, 1, 1, 0.
Okay, I think I agree with that. Can you all see that? That's the way to interpret this diagram. Correct. Now, how do we create the logic expression for F? That's a bit tougher.
Can we guess?
Sorry?
Can we guess?
Yes.
So F is true if X3 and X2, or I think X3 and X1 are true only.
Right.
We could maybe get that.
Does anybody agree, disagree? Got another. I won't write down what you said because I wasn't too sure what you were actually going to say.
It's on for an even number of inputs.
Yes, it's a so-called even function. You're right.
Like usually that would be with an XOR gate, but you have to make an XOR gate.
You've been here before. Well, you know about this. Very good. Go on. The rest of the class will become informed. You will learn it. Yeah.
I guess I'm just having a look at the table. I don't know how right this is. If x1 is 1, the result is the XOR between x2 and x3.
Mm-hmm.
If x1 is 0, then
Mm-hmm.
it's the not of the XOR between.
Right. Very good. Okay. Yes, all of you are correct, although the latter 2 speakers are right, and I don't believe them that they've never done any logic design before. For the rest of you, you're being honest about not having done, or you're too shy. So what effectively we need to do is say, look, F is only going to be true when x1 is 0, x2 is 0, and x3 is 0. Or when x1 is 0, x2 is 1, and x3 is 1. Or when x1 is 1, x2 is 0, and x3 is 1. Or when x1 is 1, x2 is 1, and x3 is 0. So we could write that out. Not x1 and not x2 and not x3, or not x1, x2 and x3, or we have x1, not x2, x3, or x1, x2, not x3. Right? So that's a logic function, and we'll talk in the next lecture about how we would normally do that.
When you're writing out, if you put like f being 0.
Yeah. Because only when x1's 0 would not x1 be 1. So I need all of these three to be 1 before that whole term is 1. Okay, and that represents one of the ones in my table. In every other term, if x1 is 0, well, this one might still be okay, but these two have x1, and therefore those terms would be 0, and they wouldn't be satisfying the function. This is sort of the inverse problem of trying to find the satisfiability of this function. We know what terms it is that we need to satisfy to obtain that function. Right. In VHDL, we would express this slightly differently. The critical statement would be the signal assignment statement, which would be, we'd have to write this out, not x1 and not x2 and not x3, or not x1 and x2 and x3, or, and so on, right? Two more terms, and then finally we'd have to have a semicolon at the end. That would be the corresponding line that we need. The entity declaration in this case would be what? What ports do we have? And they're of node in, and they're of type bit as far as we know at this stage. And we would have F as being an output bit, right? So I don't think we'll go into the details of writing that out. Now, we heard some other guys say, well, actually that can be thought of as the exclusive OR operation, and that's true. So we won't go into the details of how this is figured out at this point in time, but it would be equally correct to say that F is equal to not x1 and x2 exclusive OR x3, or x1 exclusive OR x2 exclusive OR x3 NOR, right? And it just so happens that, well, we could substitute for this bit here A, for argument's sake, then this becomes not A here. And that in turn is the exclusive OR of x1 and A. And so we could just write x1 exclusive OR x2 exclusive OR x3. Don't need a semicolon there if we're writing that. Right? So for those of you that observe that, that is true, and we don't need the parentheses then either, because exclusive OR is associative, commutative. Go on. Yeah. Associative.
When you sub 3 zeros into that, don't you get 0?
Sorry?
If you sub 0 for x1, x2, x3, when you get 0 and not 1.
Into this expression.
No, into the one that the XOR
Right, if I substitute 0 for x1
And x2 and x3.
and x2 and x3, well, taking the parentheses, 0 exclusive or 0 would be 0, right? I don't know.
I think the whole thing is,
Should they all be knots?
it should be not over the whole thing, I think. Yeah.
Why over the whole thing? This is true. Oh, yeah, no, that should have been not. And this should have been like that, I think. Is that right? Yes. So I got that wrong. This line was wrong because we have up the top here, not x1, this bit here is not x1 and x2, x nor x3, okay? So what have we got here? So that's the x nor of everything. So this should just be a not over the whole thing. Yes. Correct. Sorry. It's really hard to see sometimes when you're up close. Keep track of it. Right. Are there any other questions or comments? So look, don't feel this is beyond you. This is more advanced. We won't talk about exclusive ORs for another couple of weeks probably. Probably third week or so is when that becomes a little bit more important. So sorry for confusing you and being wrong. Right, any other questions or comments? All right, let's leave it at that. Oh, yeah.
So you said that the HDL is not case sensitive.
No.
Will we be marked on style in terms
Yes.
of...
If you've looked ahead, the labs are there and every one of them gives marks, 1 mark for style, yeah. Yeah, which sometimes is a quarter of the marks.
Okay.
Yeah. Yeah, I feel it's important enough to be able to read it. There are tools that generate VHDL as well, and sometimes what they generate is just completely unreadable, which is not particularly helpful. But I think at your level, you're meant to be able to explain to others how your design works, and the only way that you can do that really is by having it set out in a legible way. Okay? Any other questions? All right. Thank you, and we'll see you on Friday. And as I say, there'll be like a 10-15 minute intro from an Optiva dude. Right.
I guess I should say the only experience I have with FPGAs is a limited thing I did at the Optiva office once.
Oh.
They let us play with one.
Okay. So did you do their?
Focus, yeah. They made.
I only heard about it the other day, and I think they'll mention it on Friday. Was it good?
Really fun. That was the most fun I had.
Oh, great. You should tell them.
Yeah, but I think one of the hard things is how do you, since everything is like, well, like it's not a programming.
Well, it's describing hardware where things have to happen at the same time.
How do you deal with like
Like state.
yeah, like for example, like you stream bytes over a network.
How do you sequence them?
That still has to be a sequence there, right? So how do you?
Which bit has to be? So I'm not too sure that I don't want to be confusing you, but essentially. We'll talk quite a bit about state when we come to so-called finite state machines, and they're a structure that we use for sequencing operations. So that's how you control which bits are going to happen when, because you can, with a finite state machine, assert control signals that will determine which pieces of hardware, which components get activated in each clock cycle.
I think it's just hard to think about because everything with FPGAs
maybe I don't really know what you mean by static.
As in written out, like not conditional on something that happens as like a program.
I think that's probably just the nature of the examples that you've looked at, which early on you have to start with the combinational stuff whereby everything's just a function of the inputs, a direct function of the inputs. But in order to build more sophisticated hardware, you have to sequence operations. You have to be able to remember a previous state, because the sort of circuits you're talking about don't have any memory. You change the input and the output changes directly. It's like a linear relationship between the two.
I think that's what it is. Everything's pure. There's no.
Yeah, well, wait till you get to finite state machines. They will begin to talk. So once we've covered off the theory to dealing with combinational hardware, we'll get onto sequential systems which have memory in them as well, and that leads to the design of finite state machines, which are how you implement the controllers for hardware.
It's very exciting.
Yeah. Okay. No worries.
I'm a postgraduate student, so I'm actually in a wait list.
Yes.
So, but I think the student almost maximum is 10.
Yes.
So, I might have chance to join.
I
this.
can't tell you.
You can tell me.
Cannot tell you.
The
If the wait list on the undergrad side clears, then we can accept more postgrads.
only other student this room.
Yeah, look, I don't have any control over it myself anyway. I don't even have control over what lecture theories we use, and therefore what size we can accommodate. So unfortunately you just have to wait. And if it's not cleared by the end of this week, probably not going to clear.
Okay. So
Okay.
actually I'm a CS student. Yeah.
I can't help. I'm sorry.
Yes, it's fine.
Yeah.
I have an M series MacBook, and I heard that we will need to get. There's no.
Cannot get the tools working
yeah,
on
so
it.
the question I had is, like, what are the minimum specifications of Windows or like Linux?
That's a good question.
That you would recommend.
So on the web,
Yeah. The 32 gigs of RAM and 1 TB SSD.
you've seen
Yes.
the hardware
Yeah,
recommendation?
because I'm also in CompEng, so I
Yeah.
just generally looked at that.
Yeah, good. I don't know what, that's the minimum recommended by AMD Xilinx as far as I remember.
Yeah.
I'm pretty confident it will work with less,
Yeah.
but you might have to wait longer. Although the designs that we're doing are not terribly complicated,
Yeah.
who knows? It might spit the dummy at any point in time.
The question is, so does the GPU or the CPU particularly matter?
No, not at all.
Not at all.
Not
just,
at all.
Just the amount
I
of
don't
storage?
think the tools make use of the GPUs if they were present. I might be wrong on that, but I don't believe they do.
Even if you have like a relatively recent CPU, it should be fine.
Yeah, absolutely.
And
So I'm using an i5. It's a relatively low spec.
yeah.
Like I think for a grand, the sort of computer laptop you'd buy for $1,000 new
Yeah.
would probably be adequate.
Just the 32 gigs of RAM, I think
Yeah.
that's what I saw as the more important part.
Like it is memory hungry.
Yeah.
Having a lesser CPU will also slow you down, obviously.
Yeah.
But it's the memory that it does use up a lot.
Yeah. Because I was thinking like for the storage, you can obviously connect external drives, right? But the memory is the key part.
Yep.
And will this be for my whole pro degree because I'm doing
Well, that's what
CompEng?
we're recommending, yeah, because you'll be using these tools in 3211, 3601, and 4601.
Yeah.
Yeah. I'm sorry.
No, it's all right. I mean, I understand. It's just
Yeah,
it's
we
industry
wish
standard.
Apple would do it. But as you see, I use a Mac laptop myself. I've tried many times to get it working and thinking maybe it works now. I got an M4
Yeah.
laptop, does not work.
I went through Reddit and stuff, and everyone's tried.
Yeah.
No one can do it. Thank you so much.
They're not providing support for ARM processors yet, by the look of it.
All right, thank you.
Right, no worries.
I'm currently, so I'm starting my third year this term. I was thinking I have to do the research thesis. I was wondering later on if the course after I take this, if it's possible I could have a chat with you about a potential
Yeah, wait till the end. you might not want to have me as a supervisor. Okay, just wait. You know, it's still early days. You're meant to have finished all of your third year cores before you start thesis. Will you have done that?
Not yet. I just started
Just
Is it just,
step by step.
Yeah. Is it just like all third year courses or
All third year cores, the cores. So the core includes 3222, 3211, 3231 operating systems, 3601, four courses.
Do I have to finish all of them?
To do thesis, technically you do, yes. That's the
What if
requirement.
I had to take it with design project?
Well, design project A, you mean? I'm not too clear on what you're asking. Whether you have to take research thesis
with
with
design.
3601.
Yes. Would that be okay?
You may have to ask for permission to do it.
What would I need to prepare if I had to?
It's more a matter of capability, I think. If your results are generally good, I'd be happy to allow it.
What about extracurriculars?
Sorry?
Other stuff, side projects. So my own OS. Like if let's say I was going to join an OS research, right, or also an FPGA project that I've worked on.
So it doesn't really matter. The rules of the degree, the computer engineering degree are, and I think it's the same for all engineering disciplines. You're meant to have finished the third year core before you start thesis because you need the background, the theory, in order to be able to start the project. So look, there's always room to discuss, but you need to, when the time comes, have a good argument as to why you should be allowed to do that. Because it would really only delay your thesis start by one term if you waited until after 3601.
But can I take A and B together?
A and B what?
Research
No.
A and B.
No.
Because I've seen majors that do that also.
Civil engineering, I think, has a different structure that we don't. We have a 3-term structure currently, and it'll go to 2 semesters when we go back to semesters. Yeah. Sorry, them's the rules.
I didn't quite understand how we went from truth table to this part. Yeah, the next one.
Well, for every one, so we will go over this in coming lectures. It was a bit advanced, a bit unfair to do this. But for every one that you see here, you're including that row of the truth table in your function there. And just storing them together.
Which one's that then? Because this
Not x1, sorry, this one here, not x1 and x2 and x3.
Oh, so we're taking that as not.
Yes.
But
When
in
X1 change, depending either 0 or 1, it'll change the
Yes. If x1 is 0, then it depends what the value of x2 and x3 are as to whether this term will be 0 or 1. For this term to be 1, we need x1 to be 0, x2 to be 0, and x3 to be 0. Yeah? So essentially you're transcribing the corresponding rows, and we will talk about this on Friday actually, this comes up in the very next lecture, that we're transcribing the so-called min terms for the function over here. Okay?
Thank you.
Better rub that off actually. Yeah?
Yeah, so I had a few questions.
Yeah. Go on.
So firstly, it's related to the first question related to the textbook question I asked.
So what's the question?
Yeah, so the
So as I said, I haven't got that at the moment. And I don't know when I might have the time at this stage.
No, I found an old one for 21 term 3.
For 21,
Term 3.
okay.
Which has relatively the same topics.
Yes, it'll be the same topics, and so that's the references in the 3rd edition of the book. So if you've got the 4th edition of the book, it'll just be a matter of looking at whether those topics are the ones that are covered by the lecture. But if I get time, I'll go through it. So you're saying I just have to have a look at an earlier. I think I dropped them when the 4th edition came along because they weren't relevant anymore. Yeah. Oh, good. Well, that's the one I use. So there you go. It's the one that I use for the problems as well.
Okay.
Yeah. So that'll be correct. That's accurate.
Let's say I can't attend the first few lectures.
Yeah.
Would it be sufficient for me to read the textbook for
Yeah.
the
Yeah. The book is excellent, and I follow the book. So what I talk is what I can remember from the lecture or the relevant chapter in the book. So if you prefer to read the book, please do that.
Yeah, that's good to know.
Yeah.
I'll be a bit busier from here to come. Okay,
Okay.
second question is also related to the degree.
Yeah.
I read somewhere, or I think I've asked you personally, if we could take discrete math rather than math 2A.
Yes. Yeah, you
In
can.
the sense, okay, but when I look at my plan, it doesn't register it as a course of mine.
So when did you start your degree?
2023 last term.
2023. So you're still under the old rules, right? But you would have received an email from me saying that everybody... Sorry?
You said that it's okay to take.
Yes.
Okay, but because the system didn't.
all the old students are allowed to avail themselves of the new rules.
Yeah, okay,
So discrete maths is a substitute for 2A.
okay, that's good to know. And lastly, it's again related to the research thesis question.
Yeah.
I need to finish my research thesis like term 2.
Right.
And since I haven't, like I'll have only design P601 remaining.
Right.
Who exactly should I talk to?
Me.
You.
Yes.
And who
So you need to send me your transcript or your student number so that I can check the transcript and make a formal application. Like just ask, can I get this? You will still then need to take my answer to the nucleus when you try and enroll, because they may very well have an automatic check in the system that will say you haven't finished all of your 3rd-year core courses, therefore you can't enroll in thesis A.
would being a sponsored student help?
Sponsored? No, not really. It's just a rule of the degree.
Okay.
It predates my involvement with the management of it, so I don't know.
So if I were able
The
to
sponsorship, whether you've got a scholarship or not, that doesn't matter.
Okay.
You can make a claim that, you know, if I don't finish it by this date, my sponsorship runs out, and that, of course, would be extra
It's not
extra
that, it's the visa.
justification.
Yeah.
Yeah, but students overstay or have to reapply for visas all the time. So that's quite a normal thing,
Okay.
that you wouldn't be stopped from reapplying.
Okay.
But
what if I get a very good mark? in
look,
this
like
course?
I said, I would look at it from the perspective of your capability and make it dependent upon that.
Yeah, so what would you look at? Like, let's say I'm very good at computers.
I would be looking at how you've gone in the other cores for computer engineering. The computer engineering specific ones. 322, 3222, 3211, 33601, well that's one of the cores, so can't look at that. I'd look at DESN 2000. I might look at COMP3222 as well.
251.
Sorry?
Data structures design.
No.
Okay.
Software.
So, what would you consider a good mark?
What would I consider a good mark? 70 and above.
Oh, that's it?
I think so.
Really?
Yeah,
Oh,
that's a good mark.
I was so confused. Okay.
All right.
Thank you so much. I'm sorry for...
Just write to me and request that rule be waived so that you can complete your degree in 2nd term. If you've got no other courses and it would mean an extra, an extra term, we're usually pretty lenient. Okay?
Thank you.
No worries. Where are you from?
Saudi Arabia.